Okay, everybody, we alive. Now let's quickly go through the things. I want to quickly go through the things, and we know that it's not going to be hard. It's not hard for us, okay? So we should go paper by paper, discuss, do anything that we need to brush up. Let me make sure I show you guys something. Um, we should be able to do this no problem at all. This is not a problem for us. Let me show you. We start with this, obviously. Give me a second. Give me a second. Right. So this is not a problem. Let's go through these questions, and we see how it goes. Now, if you remember, the topics that we want to really look at are topics chapter 5 and chapter 6, which I'm going to remind you as we are doing. Chapter 5, remember, chapter 5. Chapter 5 is chemical energetics. Chemical energetics. Then we have chapter 6, which is chemical reactions. We want to go through these the questions from these chapters as quick as we can. And also chapter 3, stoichiometry. I'd love to take you through this. And chapter 11, organic chem reactions, organic chemistry, but I will only focus on reactions. I won't really touch anything else. I'll do the others. Right. Have you seen this? Simon, are you seeing this? Right, let's go through these questions paper by paper. Let's just see how good we are. Let's see how good we are, and let's see what needs to be touched up on. Let's see what needs to be touched up on. So I'm going to remind you as we're going through them, and we'll see how it goes. Here is the first question. This is the first paper. So if you look at number 1, okay, we're just going to be browsing through and we talk about it. Well, number 1 is going to be a lot of things, a whole lot of things, but some questions from this number 1 are related to the things that we talked about. So some questions from here, I'm going to show you, by the way, open again as we are doing, so that you can all see again what we had said. So some questions from this number 1 are related to the things that we talked about, because number 1 touches a whole lot of things, but a lot of times it touches questions from the sections that we did, which is chapter 5 and chapter 6. Okay, look at this. Let's quickly go through it. It says, tell us this question, catalyst in the Haber process, is from chapter 5 and 6. Okay, we'll open again and I'll show you. Here, here's a blue anion. Okay, this one again is from chapter 5 and chapter 6. I'll show you. Here, it's from chapter 11, the reactions. I'll show you. Forms a green precipitate when aqueous, dissolves in aqueous. Okay, so it's these 3. Right, let's go. Let's talk about this. Look at this first question. If you remember, if I show you, chapter 5 and chapter 6 was this. Look at this. Don't let me down, eh? It was, the first part was about rate of reaction. And what you needed to really know was the factors, the 5 factors that affect the rate, and how to talk about them using the collision theory. This is the part which I would need you to, by the way, when it says the importance is core, I didn't mean to say it's core chemistry. I just meant to say that it's very important. It's very important. When something is of core importance, that means it's very important. Are we together? Okay, sorry. Kingsley, I'm going to hang up just now so that you can be able to. Um, sorry. Okay, so what we were saying was we just have to know if it's rate of reactions. Remember, this is this is chapter 6. All these things that I'm showing you are from chapter 6. Chapter 6 about about three things, okay? For us to know chapter 6, you have to know rate of reaction, then you have to know equilibria, and then you have to know redox. If you know those three, then you know chapter 6. Chapter 5 is about chemical energetics, which I'll show you for those who need to see it. But here, what you need to remember is this. What is hard? Okay, because I want you to now get to a point where you start saying, which part is the hard part? I don't want to just do the basics, because the basics you've been doing them many times. We want anything to do with collision theory, Simon, anything to do with collision theory, and the 5 factors that affect the rate, and how you talk about them using collision theory. That's important. When you talk about rate, we are only interested in one thing, which is the speed at which a reaction is happening. And there are 5 factors that affect the speed at which a reaction is happening. And all of them, if you put them, the 5 factors, look at them. Let me take you to the page. Here. Look at them, the 5 factors that affect rate. Okay? And then you just have to talk about them using collision theory. The 5 factors, the 5 things that affect speed of a reaction, the rate, is concentration. That is if you have a solution, right? Concentration, you talk about concentration. Then you talk about pressure. Then you talk about surface area, temperature, and catalyst. All 5 affect the rate in the same way. If you increase concentration, the rate will increase. If you increase pressure, the rate will increase. If you increase the surface area, the rate will increase. If you increase the temperature, the rate will increase. If you increase the catalyst, the rate will increase. Can you see it? Okay. So, we used to call it like this, CCPST, which is concentration, catalyst, pressure, surface area, then temperature. So CCPST is about the 5 factors that affect the rate of reaction. They are called CCPST. Are we together, students? Good. You must know them. And now, when you are talking about them, remember, collision theory just talks about what causes a reaction. And it says 3 things are needed for a reaction to happen. That's what collision theory says. Remember it. Don't let me down. And here, I don't want to waste time on this. Okay? You can check it on your own. Let me see. Okay, let me hang up. Let's go to collision theory here, where it just tells you here to say for a reaction to happen, 3 things must happen. Particles must collide, and they must collide here. This is the collision theory. Look, it just states that for a reaction to happen, 3 things must happen. Particles must collide. They must collide with enough energy. And you can be asked, what do they mean when they say they must collide with enough energy. It means your particles must have energy that is either greater than or equal to the activation energy. Activation energy is the minimum energy required for a reaction to happen. So particles must collide, and they must collide with enough energy. What do you mean? Energy that is greater than or equal to activation energy. And they must collide in the correct orientation. So particles must collide. If they don't collide, there will be no reaction. Not only should they collide, they must collide with enough energy. And they must collide in the correct orientation. Now for each 5, and that is what we'll be calling a successful collision. A successful collision is a collision. And that collision will be with correct energy and with the correct orientation and with enough energy. So don't forget that. An unsuccessful collision, it means only the first condition has been met, or only 2 at most. If you have an unsuccessful collision, it means they have collided, but maybe their orientation is wrong. So maybe they collided, and they collided with enough energy, but their orientation was wrong. Then that collision will not result in a reaction. Or they collided and their orientation was correct, but they did not have enough energy. Then that means no reaction will happen. All 3 should happen for a reaction to happen. This is what we call a successful collision. All right. Good. Now the 5 factors, when you see them talk about it here. How does concentration affect the rate? The higher the concentration, the faster the rate. How or why? Using the collision theory. Why do you say when you increase concentration, the rate also increases? It's because what? You have more particles, which means more collisions. Okay? More particles results in more collisions. And more collisions will lead to more successful collisions, and the rate will increase. So concentration here, it's the number of collisions that will increase. Why? Because there are more particles. So everybody, more conc, more particles, which means more collisions, blah, 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 blah. When you increase concentration, you are increasing the number of particles. What about pressure? What do you say? For pressure, please, everybody, don't say more particles. Okay? Don't say more particles. Don't say more particles. More pressure, it means less volume. Particles are closer together. So it's not more particles. More pressure, this means particles are closer. Are we together? Particles closer together. And that means you have, again, more collisions, which leads to more successful collisions, which leads to a higher rate. Surface area now. More surface area. More surface area. How do you increase the surface area? By grinding things to smaller pieces. More surface area, I want you to say, more particles exposed. More particles exposed. Then you can now say more collisions, more successful collisions, higher rate. Right. Temperature now. This has nothing to do with particles. We have ended particles. We talked about particles where? On concentration. We talked about particles where? On pressure. We talked about particles where? On surface area. But temperature has nothing to do with particles. More temperature, according to collision theory, more temperature, more energy for collisions. More energy. More energy. Which means you have 1, more collisions, and 2, more energy in the collisions. Which means you have more successful collisions. Temperature, you have number of collisions increase and the energy of the collisions. So you have number of collisions and energy of collisions increasing. Then what about catalyst here? It just gives an alternative pathway with lower activation energy. With lower activation energy. So catalyst, you have now lower activation energy, which means more particles have enough energy to react now. More particles now have enough because the activation energy is lower. Yes, yes. Question. I am. You can see it. Okay, good. You can check. Check and tell me. So this is what happens. Anyway, now let's go back to our past paper. Let's see. Let's go back to our past paper. This was me just reminding you about rate of reaction. Let me just remind you one more thing. Collision theory, you're done. This is what is important. So I'm not, the investigations and stuff, we'll talk about them later. Let me go to this next section, which is equilibrium. For equilibrium, we talked about it recently, so I'm not going to talk about it too much. For equilibrium, what you just need to know, of course, you must know some of this. What is hydrated cobalt? There's cobalt chloride and copper sulfate. Copper sulfate, when it's anhydrous, it's white. When it's hydrated, it's blue. But when we go to cobalt chloride, where is it? It's blue, then pink. Here, cobalt chloride is pink when hydrated and blue when anhydrous. It is blue. Can you all see? Cobalt chloride. Cobalt chloride, when it is hydrated, it is going to be pink. But copper sulfate, when it's hydrated, it will be blue. So blue for cobalt chloride means there's no water there. When you put water, it is going to be pink. Sorry for this thing. So this shows you that when you burn it, it is going to become, to lose the water and go blue. And go blue. Now, the last thing that we see, by the way, they ask you closed system. A closed system means nothing enters, nothing leaves. That's a closed system. Okay? Closed system is a system where non-reactants or products cannot escape. None of them can escape. Now, if I go to here, what you needed to know here is the factors. We saw the 5 factors because I need to get this out of the way. I need to get this out of the way for good. Here, what I need you to know is the 5 factors that affect, this is the last, there are 4 factors rather, sorry, 5 factors that affect rate versus the 4 factors that affect equilibrium. It's actually 3, but we write them as 4. So let me say 3, because this one does not affect this guy called catalyst. So here, we do not talk about surface area. Surface area, don't talk about it. For equilibrium, it does not affect the position of equilibrium. And you don't talk about catalyst. Catalyst does not affect the position of equilibrium. So it's only 3. Temperature, pressure, concentration. So our CCPST, you should practice CCPST, is we now don't have catalyst and we don't have the surface area. All right, good. So it remains concentration, pressure, temperature. temperature, the main ones. Concentration, does it change equilibrium? Yes. Pressure? Yes. Temperature? Yes. Okay. So now you have seen this. For temperature, we said you look at the direction. Which one is endothermic, which one is exo? When you increase temperature, it will go in endothermic to reduce it. When you decrease temperature, equilibrium will shift to exo to release more. That's key. When you are talking about pressure, you look, this is Le Chatelier. Le Chatelier says, if something is changed in a system at equilibrium, then it will oppose that change. The equilibrium will shift to oppose that change. So if you increase the temperature of a system which is at equilibrium, then we expect it to shift to oppose it. You have increased, it must oppose that. Equilibrium will shift to reduce it by going in endothermic. When you decrease temperature, equilibrium must shift to oppose that. It will go in exothermic to oppose that. Pressure, for pressure, you look at the side with number of moles. Which side has number of moles? If pressure increases, then it will go to less number of moles. If pressure decreases, it will go to the side with more moles to increase the pressure. So it will be just fighting. Then concentration, we just said, if you increase concentration on the left, equilibrium will shift to the right. If you increase concentration on the right, it will shift to the left. It's just like that. So this is easy. Anyway, now we can go to, you have seen about equilibrium. And by the way, when you do equilibrium, this is where you do the important processes, which you are being asked about just now. Haber process and the contact process. Right? Haber process and contact process, if we can compare them. Where is the table where I put to compare? But here you can see the Haber process. Haber process is what produces ammonia. And you must know the stages. What is happening here? What is happening? I did it in the last lesson. We'll do it when we meet a question. What you must know for now, you should know. So when you are knowing Haber process, let me tell you right now. This is chapter 6, right? Chemical reactions, which we have seen already, the rate of reactions and what you must know, the 5 things, and how to talk about collision theory. How do you explain the 5 factors that affect rate using collision theory? That's the hard part. Then you come to this, which you saw. I just was showing you about equilibrium, and I showed you that you must know the 3 factors that affect it, and you must know Le Chatelier. Then you must then know the Haber process and contact process. When you say you know the Haber process, listen. When I say, well done, you now know the Haber process, it means you know 3 things. 3 things. For you to say you're good at the Haber process, it's 3 things. Number 1, the conditions. Okay? Everybody must know the conditions. Number 2, the stages, what happens at each stage. Then number 3, the reasons for the conditions. Because they will ask you, why 200 atmospheres? You must know that there's 200 atmospheres in the Haber process. Now you should know why. You must know they use an ion catalyst. Then you must know why. Why 450 degrees and 200 atmospheres? Why? That's the part. That's the last part. Okay? Are we together? The stages, then these conditions, then why? So 450 degrees Celsius is the same. For contact process, Haber process is the same. It's 450. But what changes is Haber process uses 200 atmospheres, whilst contact process is only 2 atmospheres. Then catalyst here is ion catalyst. Okay, we'll talk about the stages. But here, if you go to contact process, okay, the conditions, the reasons are here. We'll come to them when we need them. We'll come to the reasons when we need them. I want to go to contact process. Here, contact process. For contact process now, you must know the stages and the 4 reactions. 3 stages, 4 reactions. Then you must know the conditions. Okay? And why? Here are the conditions. Same as Haber process, 450 degrees, but only that Haber process uses 200 atmospheres and this one uses 2. Then the Haber process uses an ion catalyst, this one uses a vanadium pentoxide. There we go. That's the differences. You must know. Then you must know the reactions. What is happening at each? Let me. Because you can be asked. Give me a second. 1 second, everybody. Make sure the number in the class doesn't go down, everybody. Make sure the number of students in class doesn't go down. Make sure the number doesn't go down. It's important, eh? Now I'm having to call people over and over again. Anyway, you should know the 4 reactions at each stage. So what we know is that hi, please join. It's lesson time. All right, good. So we were saying here you should write quickly to say why I don't know why I didn't put for you the reactions. Did I put it somewhere? I think I did. What happened to these pages? Okay, I didn't put it, so let me put it. I'll fix after this. You should put the reactions on each stage. This one, we know that you have sulfur dioxide being formed. So sulfur meets oxygen. Anyway, then at stage 2, that's where the main reaction happens, right? Where you have sulfur dioxide meeting oxygen to form sulfur trioxide. So yeah, it's like this. Then you can balance it. You can just balance it. I think there's a 2 here and a 2 there. Right. Because it's a reversible reaction, this is the most important one. This is the important one, okay? This is the important one. This is where you see the 450 degrees. This is where you see the 2 atmospheres. This is where you see the vanadium pentaoxide, like this. Then stage 3, this is where you now have this is now where you have we say sulfur trioxide plus sulfuric acid to form here we call it oleum S2O7, which then goes on to form, when you dilute it, it goes on to form, you dilute it with water, right? You now form a lot of sulfuric acid. Right, so these are reactions that you must just know. And you should know that at stage 2, that's where the important one happens. Then you have at stage 3, the other 2. Okay, this is what you must know. And you should know why the conditions are used. These are the questions they ask you. So for contact process, you must know Of course, we are producing sulfuric acid. You must know these reactions we've just done. Then you must know the conditions and why they are being used. Now, okay, that's good. I'm happy with it. Let's go to do some questions and see. Here is the paper from last year. Okay, we do it together. Let's go for it. What is the catalyst in the Haber process? Tell me, guys, what is the catalyst in the Haber process according to what we've just done? Iron. Right? Right. Which chloride is blue when anhydrous and goes pink? It's cobalt chloride. We saw it there. Which catalyst is used? Okay, this is chapter 11. We'll talk about those reactions later. Right. Then if you go to number 2, so number 1 was just asking you around everything like that and stuff. Then if you go to number 2, it was now asking here, ore of aluminium, blah, blah, blah. It is extraction of metals. Extraction of metals. Extraction of metals. Then here, acids and bases. Pardon? This is the 2026 paper 42. February, March 2026. Okay. So here, if you look, let's just analyze as we are going, because some of them we're not answering them now, but we can see this is about extraction of metals. Okay, fine. Here, this is to form salts, acids and bases. Because you learn about these oxides when you do acids and bases. You learn about these oxides. All right, good. So we'll talk about them. We'll talk about them. Now, if you come here, this is about electrons, electronic configuration. This is the topic of atomic structure. Let's just say atomic structure and electronic configuration. All right, that's fine. We are analyzing the paper together. Here, this is about groups. So I want you to write to say group chemistry. I'll talk about the groups with you. Group chemistry. We see the groups and the properties you must remember. This is bonding and stuff. Now, we come here to the topics which we have been talking about. We have been dealing with these topics, but this first one is from chapter 5. So I want you to confidently approach these questions and do them. You're fine, you know them. Let me see if I want to show you what I showed you as important from chapter 5. Students, let's see what we talked about from chapter 5. Give me a second. I want to open it and show you that there's only one important thing. Hi, Antonisha, I can see you. I can see you from YouTube. Right. Give me a second. I want to show you the one thing which we talked about. And we do question after question, of course. All right, let's open it. It's only one important thing that you must know. These are the notes I made for you, from chapter 5. And it talks about endothermic, exothermic, what are they, blah, blah, blah. It talks about a lot of things. But then, it's not a lot of pages, okay? If you see, it's not a lot of pages, actually. What I want you to master is here, okay? We'll master these graphs. They are called reaction pathway diagrams. And we should also master here bond energy calculations. Bond energy calculations. This is the part where I want you to master. And I want you to master using this formula which I've put here. This delta H is energy of products minus energy of reactants, which if you come here, that's the same thing. But I want you to put it like this. This one, it's energy of reactants minus energy of products, like this here. Energy in to break bonds of reactants. Then you subtract energy out, energy of products. Energy is released when products are being formed. So this is what we are going to do. Energy in to break bonds of reactants, then minus energy out to form bonds of products. We're going to talk about it. So if you come here now, here, the first thing which they did was ask us a bit of theory, okay? A bit of theory which we talked about in the other lesson. So I won't overdwell, but we want to do it together. State how the information shows that the reaction is reversible, number one. Then number two, tell us how it shows that the reaction is exothermic. So the first one is show us how it shows that the reaction is reversible. Then show us how it shows that the reaction is exothermic. Right. Being reversible depends on one thing. It depends on the double arrows that you are seeing here. These ones here. This confirms to you that this is reversible. When you do those double arrows, it says this is a reversible reaction. Are we together? Students? Students? Hello? Hello? I want you to say the reversible arrow, which is this one. This shows, or you can say the double arrow, it shows us it's a reversible. What about what shows us that this is exo? You look at this delta H. This delta H, we know that this is a reversible reaction. This delta H is for the forward reaction. So here, the forward reaction has a negative delta H, which means it is an exothermic. When your delta H is negative, we are not happy. It means you are releasing heat to the surroundings. So here, delta H is negative. It means you are releasing heat to the surroundings. That is why we know it's exothermic, because the delta H is negative. Are we together? Okay. Now we come to this. They are testing. Do you know Le Chatelier? Are we surprised? No. This is what I've been training you to say. When you study, there is a part which comes. This part here, which is talking about Le Chatelier's principle, we expect it. And we expect questions on collision theory if they are talking about rate of reaction. Here we expect on Le Chatelier's principle. Then for bond energy calculations, we expect them to ask us to calculate the energies. We expect that. Okay, so we are not surprised. Kelly, are we together? Kelly? Should this Le Chatelier shock you, Kelly? Should it shock you? Are you shocked that you have gotten a question which needs Le Chatelier about temperature and pressure and catalyst and things, how they affect position of equilibrium? Are you shocked? No, you're good. You're not. You expect it, Kelly. You expect them to ask you about those on equilibrium. That's the part which comes. So that's the part which you should read over and over again. Here they are now saying, for this reaction. So always look at your reaction. Don't say things from the head. You answer using this one. Then you can see what they are doing. Then you will know which side they move, which side the equilibrium will move. Here, temperature is decreased. Temperature is decreased. Remember, Le Chatelier says that when you do a change, the system must fight that. The system must fight that. When you change anything, the system must fight that. That's what Le Chatelier said. So here you are decreasing the temperature. We expect the system, oh hi, Anesu, I just saw you. Okay, great. So when you decrease the temperature, we expect the system to fight and increase it. Now, what is to increase? How does the system increase it? It promotes the exothermic reaction. Exothermic reaction releases heat to exit. So here temperature is decreased. So temperature is decreased. The exothermic reaction must be promoted. So here, which is the exothermic? Remember I said, listen, I said the one they give you here, this delta H they give you, is for the forward reaction. For the backward one, we can even put it here for jokester, to say this will be 40. You change the sign. If this one was negative, this one will now be 40 kilojoules per mole, the positive one. This is for the backward reaction. This is for the backward reaction, which is this one. Forward is this one. Backward is that one. Right. Are we together, students? So now, temperature is decreased. Remember, forward reaction is exo. Backward reaction is endo, which means it worsens the situation. Endo is a reaction that is greedy. It takes up the temperature. So here when temperature decreases, you can't go to endo. Endo is going to take it even more. The equilibrium should oppose that, not worsen it. So temperature is decreased. Equilibrium will shift to exo, so that exo will fight that. Exo will now start to increase the temperature, increase, to fight what has been done. So if you come to this system and decrease the temperature, you're going to start getting more water. Water gaseous is steam. You start getting more steam, and you start getting more methanol, and you don't know why. It's because the equilibrium is fighting you. So, effect on concentration of methanol. Here, there'll be more methanol. Remember, this here is the methanol. So, we know that if you reduce the temperature, it is going to shift to the right, to exo. It will promote the forward reaction. So, equilibrium shifts to the right. What does it mean, students? You are chemistry students. When we say that it shifts to the right, it means we are going to start getting more of these ones. So we are going to start getting more of them because it has shifted to the right, to the direction of exo, to try and increase the temperature. So effect on concentration, the concentration increases. The concentration of methanol increases because the equilibrium has shifted to the right, to the exo. So you are now getting more methanol. Come on now. Then here they say effect on rate of forward reaction. What is the effect on the rate? Remember, when you increase concentration, rate increases. When you increase anything, those 5 factors, this is now rate. Hello? We have 2 things that I showed you. I showed you rate and the 5 factors that affect rate. And for rate, we were using collision theory. It's completely, it's not Le Chatelier. Le Chatelier is for Equilibrium. So don't let anyone make you be confused. You know better. You tell them, hey, stop mixing up your chemistry. Something is still wrong with your chemistry. Your chemistry is still mixed up. Equilibrium is a completely different subject to rate. When you talk about rate, it's just the speed of the reaction. And there are 5 factors. And when you increase the temperature, we said you'll be increasing the speed of the collisions, and you'll be increasing the energy of the collisions. But here we have decreased the temperature. So what do you expect? The rate will decrease. The rate will decrease. The rate will decrease. It's not happy. You have decreased the temperature. So the collisions have less energy, and you have less collisions. What about pressure now? Pressure in the reaction vessel. That means the pressure of what is decreased. You are decreasing the pressure. The pressure goes down. When we talk about rate, of course, rate will decrease. So let's start with rate. Rate is easy. The catalyst is removed, the rate will also decrease. Because when you add a catalyst, the rate increases. When you remove a catalyst, the rate decreases. But equilibrium is not affected by a catalyst. Catalyst only affects how fast a reaction happens. It doesn't affect equilibrium at all. But when you now change the pressure, then how do you talk about Le Chatelier? This is where we see, did you hear me or you did not hear me? Because we talked about this. And we said for pressure, you look at the side with moles. You look at the number of moles. Here we have 3 plus here 1, which means we have a total of 4 moles this side. Here we have 1 plus 1, which means we have a total of 2 moles. We have a total of 2 moles on the products. Then we have 4 moles on the reactants. 4 moles on reactants, 2 moles on products. So that means we have less on the products. So the only time we come to products is when we want to reduce the pressure. If pressure is now too high, then we will go towards product side. Here it is more. This is more because it's 4 moles, which is more than 2. So we only come here when we want to increase the pressure. That means we come here if anyone reduces the pressure, then we are going to shift to the left. So here we have reduced the pressure. We have reduced the pressure. So now the system will fight that to say, hey, wait, why are you decreasing the pressure? Le Chatelier said the system will now fight that, what you're doing. So what do we expect the system to do? It should go to the side with more moles. More moles. That means we start getting less ethanol, less methanol, okay? Because the equilibrium will shift to the left, and you start getting more carbon dioxide and hydrogen to try and increase the pressure. So this one, it decreases. The effect on methanol, it decreases. The methanol. Because we will start getting more carbon dioxide and whatever. Equilibrium would have shifted to the left. Yeah, this is a sign. It's testing you to say, are you mastering Le Chatelier? Are you mastering? Then here, reaction pathway diagram. Reaction pathway diagram. We know that here we always have reactants. We start with reactants, and here we have products. Now, this here, from reactants to products, this is your delta H. Then from reactants to the top of your mountain. This is the activation energy from reactants to the top of the mountain. These are the only 2 things you need to label. Then reactants, then products. Now, complete the reaction pathway diagram. We have completed it. They've asked us, in your diagram, show the formulas of reactants and products. Okay. So they want the formulas of reactants and the products. Which ones were the reactants, by the way? Hydrogen and carbon dioxide. So they want us to show that. They want us to show the hydrogen and carbon dioxide. So please, you come here. You, instead of reactants, you say hydrogen, gas, plus carbon dioxide was 1 more, I think, gas. So 3 moles hydrogen plus 1 more carbon dioxide. We put it like that. Then here, 1 more ethanol, 1 more water. So here, you say 1 more ethanol, 1 more water. Right. This was gas. Well, were all of them gases? I have a feeling. Yes, all of them are gases. So you are done. You would have shown this. Activation energy, we know, it's from reactants to the peak of the mountain. Then delta H is also from reactants, but now to products. Right. The enthalpy change of the reverse reaction. They want you to show the enthalpy change of the reverse reaction. We've already put it here. We know that you just change the sign. For reverse reaction, you just change the sign. It's the exact same value. So you say it is plus 40 kilojoules per mole, the reverse reaction. The activation energy of the reverse reaction. Here, activation energy of the reverse reaction. So let's go and see activation energy. Is it there? Yeah, the activation energy of the forward reaction is 220. Can you see that? Activation energy of forward is 220. Here's what we mean. Activation energy of forward is like this. Now, when you want to do activation energy of reverse, you no longer, you want to go to the peak again, but you'll be starting from the products now. You go products all the way to the peak. This is now reverse. It is EA reverse. Here we've seen our EA to be 220 kilojoules per mole. Activation energy will always be positive. So I don't want to see a negative activation energy. It means you're doing something wrong, because it's always going up towards the peak. So here we know that I think we found activation energy in reverse. I think we found this to be positive. Is it 40 kilojoules? So here we'd be having 40 plus 220, which is 260 kilojoules per mole. Because 40 was here. For reverse, this delta H, it was 40. So when you take this 40 for delta H and you combine it with this 220, you get 260 from the bottom. So there we go. Are you seeing? Are you seeing it, everybody? So here you should write plus 260 kilojoules per mole. Now we come to bond energies. Now we come to bond energies. Are we surprised? No! I showed you the formula because I knew it was going to be needed now. So here, calculate the energy needed to break the bonds. That's the energy in. Which is the energy needed to break the bonds. Here is the reaction. They'll give you, don't worry. You should just tell us which bonds are there in the reaction. Which bonds? You can see there's a hydrogen to hydrogen bond. And how many do you have of them? We have 3 of them in blue here. So you can say we have 3 hydrogen to hydrogen bonds. Plus, what other bond do you have, Captain? You tell them, I have a carbon to oxygen double bond. We have a carbon to oxygen double bond. Then I'll say to you, how many? Then you should tell me 2 at the reactants, because we have another one here in purple. So you come and put that to say plus 2 of carbon to oxygen double bonds. This is the total energy required to break them. So this is going to be, what is the HH bond? It's 440. So it's 3 of 440 kilojoules per mole. Plus 2 of carbon to oxygen double bond is 805. Can somebody please punch quickly and tell me what answer you get for this simple question? It will never be simpler than this. Tell me, guys, what answer do you get here? Quickly, 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 everybody. Let's tell. Tell me, what is the answer here? Put it in the chat. Put the answer in the chat. Put the answer in the chat, everybody. Let's go, let's go, let's go. Participate. May I see the answer in the chat, please? May I see the answer in the chat, please, people? Let's go. What is the answer? Yes, keep bringing it in. What's the answer? Everybody else, where are you? Where are you? All right. Where are the people? Where are the people now? Letty? Put the answer in the chat, Antonisha, on YouTube as well. (2930 kilojoules). That's the energy required to break the bonds. It's called energy in. You need to break bonds of reactants. So we just looked at the reactants. That's just what we did. We saw all the types of bonds that are there. Now we are going to look at the products, obviously. And we see which bonds, because they will say energy released when forming bonds, which is energy out. You focus on products now. You focus on products now because you want to get the energy out. Now, what bonds are there? You want to see the bonds because that's how you calculate energy. It's called bond energy. So look at the bonds. Which lines do you have? I have a line which comes from carbon to hydrogen. How many do you have of such type? Carbon to hydrogen. I have another one which I'm putting in red. Then I have another one which I'll put in green. So I have 3 in purple, in green, in red, or in pink. These 3. These are carbon to hydrogen bonds. So we can say that carbon-hydrogen bonds, we had 3. Plus, here we have another carbon to oxygen bond. Okay? Starts from carbon, goes to oxygen. So we have carbon to oxygen. Do we have another one which is like that? No. Okay. So we have a carbon to oxygen bond. Plus, we have the oxygen to hydrogen. Another one here, oxygen to hydrogen. Another one here, oxygen to hydrogen. So we have 3 of them. The oxygen to hydrogen, we have 3 of them. Tell me the answer now. Let's go, everybody. Tell me the answer. Three of these carbon to hydrogen. Let's go. Okay, I'll give you to calculate. Carbon to hydrogen. Oh, they didn't tell us. Oh, so that means they're going to ask us. They're going to ask us to find it in the last stage. Anything they don't tell you, obviously, you know they're going to ask you to find it. So you can just leave it like that to say 3N. So here, anyway, it will be plus. Plus. What is carbon to oxygen? This single one, the single one, okay? The double one, we've done it, the 805. Here we want the single one, which is 360. Then plus 3 of oxygen to hydrogen, which is 460. 3 of 460 kilojoules per mole. All right, so can you get me the answer for these two at least? What is the answer for these two? This is still 3 of carbon to hydrogen. What is the answer here? Somebody, can you tell me the answer, please? Somebody, 360 plus 3 multiplying 460. What's the problem? 360 plus 3 open bracket 460. Tell me what answer you're getting. Anesu, everybody on YouTube and wherever, tell me. What is the answer now? Or Instagram? What is the answer now for this one? Would be saying now, okay, because we don't have this one. They didn't tell us, but that's not a problem. Okay, you didn't tell us, but that's not a problem. So it's still 3, we leave it as 3 carbon to hydrogen. But what we know we put. What we know we must put. So this one we know, so we must put this. Okay, so what is important is for everybody to know that energy is released at product side, and energy is needed at reactants side. They actually said reactants here. So you just focus on the things that are at reactants here, and then for energy released, you just focus on the things that are at product side. Things that are at product side. So tell me the answer, students. Let's go. I want to see the answer coming in. Let's go. All right. I'm seeing the same people though. Letty, where's your answer? I'm seeing the same people. 1740. Okay. 1740. So it's 3 carbon to hydrogen plus 1740 kilojoules. Now they say calculate bond energy of this bond. Calculate bond energy of this. Calculate bond energy of this. Simon, why are you getting 17? So now, for you to get bond energy, this is the formula that nobody should ever even dream of forgetting. Nobody is allowed to dream of forgetting. Delta H is equal to energy in minus energy out. We start with the energy in. Then we remove energy out. Energy in minus energy out. This is the most important formula. Okay. It's okay, Simon. So this is the most important formula. You use it all the time. They ask you for bond energy. You use energy in minus energy out. What is the energy in? So do we know delta H? You go to the top. You will see delta H. It will be given. But first you must put the formula, because the formula is not given. The formula is not given. Then you now go and take your delta H. Here it's negative 40. They've shown it here to say negative 40. So you say negative 40 is your delta H kilojoules is equal to, what is energy in? 2930 kilojoules minus what is energy out? 3, you put in big brackets, 3 carbon to hydrogen plus 1740. So this is what we have. It's like this. This is what we have. Now we do a bit of maths. Students, we do a bit of maths. So look at what happens. You say negative 40 kilojoules is equal to 2930 kilojoules minus 3CH becomes minus 3 of CH. Then minus of plus becomes minus 1740. And then what you just have to do to get an answer here is you take this negative 3, whatever, you swap it with negative 40. So basically it becomes 3. Okay, I was writing things that are way too big. That's why they are not fitting. It now becomes 3CH is equal to 2930 kilojoules. Then this 40 comes, it also becomes plus 40 kilojoules. Then minus 1740. Minus 1740. Because they have swapped. This has gone there. This has gone there. Then what answer do you get now for 3CH? What is the answer now? What's the answer? Put the answer. 2930 plus 40 minus 1740. Put the answer. Put the answer, everybody. Anita, Letty, Kelly, Oratile. Let's go. Everybody who's in there. Everybody who's live. Put the answer. Okay, I'm enjoying. That's good. Yes, YouTube audience, put the answers as well. So it is 1230, even Instagram. So 1230 kilojoules. All right. Now look at what you just do. You just take 3 to the other side. Obviously, everybody knows that. So carbon to hydrogen, we have found you by using the formula of delta H. So we'll use it all the time. So it'll become 1230 kilojoules divided by 3. Just that. Then what's the answer now? What is 1230 divided by 3? 410 kilojoules per mole. So 410 kilojoules per mole. That becomes the solution. We move on. Well done. I'll be happy. So, yep, these are the questions on the things that this is now organic chem now. Huh? This is now organic chem, which they're asking us. Okay, which is fine. We'll do it. We'll talk about it. Don't worry. We'll do a lot of organic chem. It's not a problem for us. We'll revise it again. Let's try to see another paper now. Let me do one more paper 4, then we'll do the paper 2s going forward. February, March for 2025 now. February, March for last year now. February, March for 2025. There we go. February, March for 2025. Let's go for it. What is meant by the term closed system? So these are the things that we were talking about just now. The things that we did when we were doing our equilibria, don't forget. And we said, so for a system to reach equilibrium, it has to be a closed system, which means reactants can't leave, products can leave. You cannot add more reactants. You cannot remove any. The products cannot. So nothing can enter and nothing can leave. That is what we mean by a closed system. If you remember, for those who remember when we did it just now. So you're writing, you're saying a closed system, a system in which no reactants or products can either leave or enter. Are we together? None of them can do that. So nothing can enter or leave. State what delta H represents. Enthalpy change. Delta H represents enthalpy change. Okay. Now, state how the value of delta H shows that the forward reaction is exothermic. Show how the value of delta H shows that the forward reaction, remember this one we said it is for the forward reaction. And for it to be exo, that means it's negative. when you get a negative delta H, it means it's an exothermic reaction, that one. So you can say delta H is negative, meaning forward reaction is exothermic. Deduce the value for the delta H in a reverse reaction. So for reaction, we know that delta H will be now positive of that because it was negative. You just change the sign. Here it was negative 105. Okay, so here it will be positive 105 kilojoules per mole. Okay, you put a capital J. You can put kilojoules per mole. Anyway, here we are now being asked about Le Chatelier. We are back. Everybody, we are back. Le Chatelier. If you have a problem with Le Chatelier, I advise you, I'll give you a link of something to watch, one of my clips, and you watch it over and over again, and I explain it, okay? I don't even mind sending a piece. Right, let's go. The temperature is increased. Remember, don't you dare try to answer for me Le Chatelier without looking at the reaction. Everything is you look at the reaction. You answer whilst looking at the reaction provided. This is for forward. You might as well put for backward. It is positive 105 kilojoules per mole. This is what? Delta H for backward reaction, which is this, the one which goes backward. Then this one is for forward, which goes this way. The temperature is increased. So what happens to COCl2? COCl2, where is it? It's a product. Oh, so okay. So the product. They're just trying to say, will the equilibrium shift to the right or to the left? When what? Temperature is increased. Huh. So you are increasing temperature. All right. The equilibrium should fight that. So it must decrease the temperature. How does it decrease the temperature? It goes to a certain guy called endothermic. It goes to the endothermic side. Endothermic takes in endo, to enter, to take in the heat. Endo is a specialist at taking heat. So here you have increased the temperature. Then that means that the temperature must be decreased now by the system. The system must oppose that, or else we are lying. Le Chatelier is wrong, which he can't be wrong. So the system will oppose that, which means it will reduce the temperature. It will fight to reduce the temperature by going in the direction of endo, which is what? The backward. Endo, the positive. If you have a positive delta H, it means you are endo. When it's negative, that's the bad one. That's the exo. You are giving heat to the surroundings. This is the exo. So here it is endo. So it will shift to the left. Equilibrium will go backward, shift to the left, which means you now have less products. You now have more reactants. It is shifting to the left, which means the concentration of COCl2 will decrease because it will shift to the left. So the concentration, it decreases. It decreases. What about if you add carbon monoxide? Well, this is easy. If you add something that is on the left, the equilibrium will shift to the other side, to the right. So you have added carbon monoxide, which is on the left. Equilibrium should shift to the other side, which means it will shift to the right, which is to the products. And you start getting more ClCl2. So that means the concentration of this increases. What happens if you increase the pressure now? What happens if you increase the pressure? What do you look at? Number of moles. Which side has more moles? So here there is 1 mole here and 1 mole here, which means 2 moles. Then here there is only 1 mole here, which means there is 1 mole. So there is less here. Then there is more on here. We are now talking about pressure, so ignore temperature. We are now looking at pressure. For pressure, we look at where is it more, where is it less. So we only go to the side with less when we want to reduce the pressure. When we go to the side with more when we want to increase the pressure. So here, pressure is increased already. We have to fight that. Lichatellier said this has to be fought. So we have to decrease. We have to go to the side with less. Which side is that? With less. It is the right hand side. So the equilibrium will shift to the right and more ClCO2 will be produced. So that means the concentration of CoCl2 will increase. It increases. Because the equilibrium is trying to reduce the pressure. What about if you add a catalyst? There will be no change. Catalyst will never change equilibrium. It only changes the rate. More bond energy calculations for March 2025. You see, you're expecting them. You're expecting them. Anyway, you know that these are the reactants, which means it is energy in. Here you have your reactants, which means energy is required to break these bonds. Energy is required to break these bonds, so it's energy in. Then here you have the products. The product, which is energy out. Anyway, calculate energy needed, that's energy in. What is it going to be equal to? Energy needed to break these bonds. Look at the bonds. Tell me the bonds that are there. It's not abracadabra. What bonds are there? You have one carbon to oxygen triple bond. So you have carbon to oxygen triple bond, and it's just one. Then you say plus. What other bond do you have? You have a chlorine to chlorine single bond, and it's just one. So you have just one chlorine to chlorine. These are the bonds you have, which is going to be. What is the carbon to oxygen triple bond? We look at the table. It is 1075. Plus, what is the chlorine to chlorine single bond? 240. And these are kilojoules per mole. What is 1075 plus 240? Tell me quickly, students. Put the answer in the chat. Quickly, guys, put the answer in the chat. Yes, well done. Equilibrium will shift to the left. You're doing very well. Zishan. So tell me, what is the answer here? Put the answer in the chat, everybody. Put the answer in the chat now. Put the answer in the chat. 1315. Well done, Kelly. I'm happy I saw your answer this time. I need the others now also to do it as well. Aki, I want to see an answer from you and Tatayaon. Let's go to now energy released. I want to see answers in the chat. Everybody, I want to see answers in the chat. From everyone all over. May I see the answers in the chat, please, when I ask? Now let's go to here. Calculate energy released. Energy released, that's energy out. We look at products. Tell me all the bonds that are there. Well, there's this certain bond which goes from carbon to chlorine. How many do you have of those which go from carbon to chlorine? We happen to have 2. Okay. So go put that. 2 of carbon to chlorine. Plus, is that the only bond? No. We have a carbon double bond with oxygen. It's not a triple now, it's a double. Okay. So we have a carbon to oxygen double bond. All right, that's cool. Now, get us the energy out, please. 2 of, do you have carbon to chlorine? Carbon to chlorine, yeah, it's here, 340. It is 340. So 2 by 340 kilojoules per mole. Plus, what is the carbon to oxygen? We look. Oh, carbon to oxygen double bond is missing from the table. Are we surprised? No. So we just say plus carbon to oxygen double bond. Somebody tell me, what is 340 by 2? Let's not waste time on this one. 680 kilojoules. Plus carbon to oxygen double bond. So it is 680 kilojoules plus the carbon to oxygen double bond. Okay. Now they say calculate the bond energy of this. We're expecting that. We are expecting them to do that. How do we find this bond energy? By using delta H. Delta H helps us now to find this bond energy that they want. Delta H helps us to find this bond energy that they want. Really? Yes. How do we do it? Well, we would be saying delta H will be the most important formula that an IGCSE student should also know for these bond energy calculations. It should be known energy in minus energy out. Any serious IGCSE student should know this. Okay, you start from here. Energy in minus energy out. You start by writing it. It's energy in minus energy out. So I'm counting on you guys. Then you go get delta H because you'll be given delta H. You then go get it. After writing that very important formula, you go get your delta H because you'll be given and you know it. Here it is, negative 105 kilojoules per mole. So it is negative 105 kilojoules per mole. This is going to be equal to, what is the energy in? Well, you just got your energy in to be 1315 kilojoules. So it'll be 1315 kilojoules minus, then you open a big bracket for everything that is now coming, because there'll be two things here. It'll be 680 kilojoules plus carbon to oxygen double bond. Okay, now we just need to find the answer. Okay, remember to write small things because you need to do a bit of working here. Now you get negative 105 kilojoules per mole is equal to 1315 kilojoules. Then you say minus of 680 becomes minus 680 kilojoules. Then minus of this becomes also minus carbon to oxygen double bond. And everybody knows what you do now. You swap this one and this one. You swap them. It goes to the other side. It becomes positive. Carbon to oxygen double bond is going to be equal to 1315 kilojoules minus 680 kilojoules. Then you say this 105, it goes to add plus 105 kilojoules. Because it was subtracting, when it goes to the other side, it should add. What do you now get as the answer? Tell me quickly now. Everybody, please punch this. 1315 minus 680 plus 105. Tell me what we are getting now. Tell me what we're getting now, superstars. Wow, that was quick, Kelly. That was impressive. Keep the answers coming. Put the answers in the chat. Put the answers in the chat. Put the answers in the chat. Let's see if it's true. Put the answers in the chat, everybody. Come on now. Yes, come on now. Put the answers in the chat. 740 kilojoules per mole, because it's for bond energy. So the final answer is like this. Well, that's good. Okay. Well, the rest is on okay, here. Explain in terms of the collision theory. Wow. We're expecting this. We're expecting a question on collision theory, so we are not shocked. I'll need to answer a call just now. We are not shocked. We're expecting a question on collision theory. Why decreasing the temperature decreases the rate? Well, we know that I'm going to help us. I'm going to send you some so you can practice, okay? You practice putting the things, because we had concentration and we said concentration decreases the number of particles. Yeah? For concentration, it is linked to number of particles. For temperature, it is linked to energy. Energy. So when temperature decreases, we are now saying collision theory stuff now. When temperature decreases, the particles lose kinetic energy. Lose kinetic energy and start moving slower. The particles lose kinetic energy and start moving slower. Okay? This reduces the frequency of collisions. In other words, the number of collisions. It reduces the frequency of collisions. Okay? And also reduces the amount, or let's say reduces the energy of particles. Should I say the amount of particles with enough, or with the amount of particles with energy greater than or equal to activation energy. You can write it like that. It reduces because the particles have lost energy. So less particles now have enough energy to actually do a successful collision. Okay? As a result, you can now say, as a result, there will be a reduction in successful collisions and rate. The successful collisions go down and the rate will also go down. So they are linked like that. Okay, so I'm very happy. I'm proud of you guys. I'm proud of you guys. Right. This is it. I've done a good number of questions. I'm going to send you something that I want you to do and practice related to these. Calculating bond energies. You do your own calculation, and you do any question they give you on energies or rate of reaction or collision theory. I want to give you, and I want to show you the keywords. Cambridge is about keywords. A lot of people go in exam, come out expecting marks, but they come out with, they don't get the marks. The reason they don't get those marks is they didn't write the answer Cambridge wanted, and they thought they did. So the most important thing is to know the specific words to use. When it's about this, it's about energy. The kinetic energy goes away. But when you talk about concentration, you talk about the number of particles. More concentration, more particles. That means there are more collisions. That means you're going to have a higher rate. And we talked about pressure. We said it's not about more particles, but when you talk about pressure, it's the less volume. Okay? Less volume. So the volume is reduced when you increase the pressure. So you have more collisions. And when we say less volume, we mean there is less space. The particles are now in a tight area, which means they start colliding more. You know that when you reduce the space, people start colliding. So when you talk about pressure, you relate it to space or volume, okay? But when you talk about temperature, you relate it to kinetic energy. And when you talk about, what is the other one? Concentration, you relate it to number of particles. When you talk about surface area, you relate it with the number of particles that are exposed. You should say those type of words when you do collision. When they say according to collision theory, that's what they are looking for. That is what they're looking for. I know you won't let me down. I know you won't let me down. Okay, that's great. Let's meet tomorrow morning, and we'll go live again tomorrow morning. We do a bit more maths. We do a bit more physics. We do a bit more of these things. I have a pleasant surprise for you. So it's the content that I've been making for you, that I'm going to share with you. A lot of content. Let's go live tomorrow in the morning very early, because during after lunch I have meetings. So let's do early in the morning. So the earlier the better for me. Okay, let me say from 8 to 10 I may have, or from 8 to half 9 I may have the engineers. So let me meet you at 10 o'clock exactly. So tomorrow at 10 in the morning is your time. Goodbye and good night. I've taken their names, I've exported them on Google Sheets because you are not a lot. You are dismissed.